Yeah, thanks very much indeed, and for the opportunity to present today as well. I'd first like to thank everybody who's been involved in this project, including the EPSRC and Innovate UK for their funding, and also UPC Cambridge for providing further advice as well recently. So the development process for pMDI products is iterative. Typical past developments could take several leaps to get to a design freeze for manufacture. There's often been minimal predictive modelling used in the aerosol physics part of device design. So the aim of our modelling work is to reduce the number of iterations by 50%, thus significantly reducing the development time, whilst also improving the aerosol performance. For pharmaceutical customers and their patients, this will also shorten the time to market as well. So this is a typical pMDI aerosol plume in free air. Typical emission times are around 250 milliseconds. Whilst the air temperature might be 25 degrees centigrade, which admittedly is quite optimistic in the UK at the moment, the HFA propellant aerosol emitted will be significantly cooler due to evaporation of the HFA propellant. We can quite easily see that the volume at region B is considerably larger than at region A. An additional effect is that the evaporation of the HFA is very important for driving down the particle size for eventual delivery to the lungs as well. And our estimator model outputs that we're presenting here are the droplet size and the areas A and B in this diagram. So if we look inside the canister pack, you can see the green metering chamber in bright green, the light grey stem just beneath that, and also the added sump, which is the crosshatch green region at the bottom there. If we enlarge the valve cross-section for greater clarity, we can see the dark green elements now, which show the metering chamber, and the stem and the sump, which together form the expansion chamber, which ultimately leads to the spray orifice down at the bottom. So if we now remove the valve, we can show only the fluid flow sections inside the valve and actuator. The estimator model here represents the device as two boxes of known volumes joined together by the stem orifice, the little white box in the middle, which ultimately leads to the actuator spray orifice. And it's the pressure in the sump and the stem which ejects the boiling formulation through the small spray orifice and then produces the aerosol. And this follows the work presented originally by Marie Harang in her PhD thesis in 2013. So the model carries out a mass and enthalpy balance across the entire device system, and this yields the vapor quality, or the vapor mass fraction, and the vapor pressure in the stem and the sump. And these two variables are inputs for Clark's formula, which I'll show on the next slide, which provide the mass median diameter of the aerosol at the orifice exit. Recipharm have got a new study underway at the moment, varying orifice diameters, sump, and various other aspects of geometry, the propellant type, and the ethanol ratio. And the output from this will verify our model and allow correlation as well. So in summary, the estimator model takes the four main inputs on the left there and yields the customer required information on the right-hand side of the box there. So I think now we've got some interesting science to come. So fundamental to our whole approach is this pressure enthalpy chart, which varies with each different propellant type. And we can represent this graph by a number of polynomials which describe the properties of the individual propellant. And we can see three regions there. There's the two-phase region in the middle, which I'll talk about on the next slide. There's the superheat region on the right-hand side. In that region, if you add heat, you just get a change in temperature. There's purely just vapor there. On the far left-hand side of the graph, fairly barren-looking area, that's the subcooled region, so there's only liquid there, no vapor. And if we add heat there, again, we just get a change in temperature. And right at the very top, we have an interesting point, the critical point, the little orange dot. That's where we get a new phase emerging, which is known as supercritical fluid. But it's the two-phase region which we're interested in here. So in this region, if we add heat or enthalpy, we alter the temperature, pressure, or vapor fraction of the propellant. And we can represent that process by a number of typically quartic polynomials. And we can calculate the properties we want using an iterative method if the other properties are known as well. So just as an example, we can calculate the enthalpy at each microsecond time step using a mass and energy balance as before, and we can iterate to calculate temperature, pressure, and the vapor fraction. So from the chart, we can see that the vapor fraction, 75 milliseconds into discharge from a 25 microliter device with just the propellant-only formulation, is 63% by volume. So we then convert that into a mass basis for the next stage. So from the calculated sump and vapor fraction, we obtain the mass median diameter of droplets immediately post-actuator, so before any flashing has occurred, using Clark's equation here. And he obtained the constant and the power shown here from an experimental study of his own back in 1991, in fact. So these are the results we get out. The initial pressure in the expansion chamber is atmospheric, so we get artificially large droplets right at the start. So if you look at the left-hand side of the graph, you can see we've got artificially large droplets there. Mid-discharge droplet size is considerably smaller due to the high vapor pressure in the expansion chamber, with a high associated slip velocity between the liquid and vapor. Adiabatic evaporation is assumed in this model, so there's no heat transfer to or from the propellant during this. Which means that towards the end of the discharge, the droplet size tends to increase again, just because the formulation cools down and the liquid gets exhausted as well. So again, we get artificially large droplet sizes there as well. So if we white out those areas which aren't the primary interest of device design, the greatest mass emission will occur in the sort of lower region there. I have to apologise for the lack of numbers here. This is unpublished data at the moment, so hopefully this will give the general gist at least. So R134A, which is represented by the dark line, shows the greatest time for discharge here. The minimal droplet sizes are actually quite similar for all three propellants there. The discharge time here is a function of vapor pressure, density, the orifice diameters, the device actuation rate, that's very important actually, and the propellant and the properties as well. So just in conclusion, we aim to reduce the development time of pMDI products by 50%. A transient time-stepped one-dimensional model has been applied using Clark's correlation as well. Predicted residual particle size and spray pattern are going to be correlated with device and formulation properties by an ongoing study at Recipharm. And using the predictive model, the aerosol characteristics can be optimized before producing any prototype devices, thus saving many iterations. So I'd like to thank everybody who's been involved in this project one way or another. All of these references are currently available. Thanks very much for the opportunity to present today, and I'll happily answer any questions anybody might have. Thanks very much.
Thank you, Ben. So in your conclusion, you mentioned it again. You started in the project with the idea to at least halving the number of those iterative cycles in pMDI development. Was that successful?
Well, this is very much a project still in process at the moment. We haven't actually implemented this part of the work. Earlier stages of the project have been quite encouraging actually at reducing the time. This is a relatively new venture, so yeah, we're still waiting to see on that, but we're optimistic anyway.
Okay, and are there any, or did you look into droplet size correlations related to Apsd or anything like that?
But yeah, we're typically going to be looking at the fine particle mass and the impactor stages in the next part of the work. So at the moment, this will just give us the propellant droplets. But as you say, we then have to correlate that to what happens once those droplets fully evaporate, just leaving the active substance behind. And that'll obviously vary depending on whether you've got a solution formulation or a suspension formulation. That we expect will have quite an effect as well. So that's going to be quite an interesting conclusion that we'll hopefully draw when we finish the experimental study as well and we correlate the data.
Okay, thank you very much. And so we are looking forward to hear more from you in maybe next year's conference. Thank you.
Thanks very much indeed.